Picture this, because I guarantee you have lived it. You have a Spark job running in production. It's dragging.
Oh, yeah. The SLA is completely at risk.
Right. So you look at the cluster configuration, and you just double the size. You throw more machines at it, but you run it again, and the job is still slow. So what do? You double it again.
Which is honestly the single most common reflex in data engineering.
And now you're staring at your dashboard. You have hundreds of executors spun up. You've allocated this like massive mountain of CPU. The memory footprint of this single pipeline is so large that your cloud provider is thrilled, but your finance team is starting to sweat.
They're asking some very pointed questions at that point.
Exactly. And despite all of that sheer horsepower, the job still crawls. It's absurd. And, honestly, it is a little bit embarrassing when it happens to you, especially if you consider yourself a senior engineer.
I really want to validate that exact experience because everyone assumes the problem in that scenario is a lack of hardware. Like when a distributed system is slow, our default industry reflex is just to distribute it wider.
Yeah, scale out.
Right. But in reality, adding more executors to a slow job is almost always the wrong diagnosis. It's treating a symptom you haven't actually identified yet.
We need to stop treating Apache Spark as this magical black box that blindly converts hardware into speed.
And start seeing it as an inspectable, transparent glass box. Because if you don't know how the physical execution shape of your job forms, you do not actually know why your job is slow. And if you don't know why it's slow, your cluster sizing is just a very expensive guess.
Okay, let's unpack this. Why is our first instinct always to just throw more machines at the problem?
I mean, to understand why we default to hardware, we have to examine what I call the psychological trap of declarative code.
Oh, that's a good way to put it, the psychological trap.
Yeah, because declarative code creates a very convincing illusion. You sit down in your IDE and you write this one clean, elegant chain of data frame operations. It looks perfectly linear on your screen.
Very readable.
Right. But Spark has to translate that declarative code into a wildly messy distributed reality. It has to figure out network boundaries, physical data movement, and all the synchronization that happens between isolated machines.
It's doing a lot of heavy lifting behind the scenes. Let me put it this way. Imagine you manage a massive manufacturing plant, right? You've got an assembly line, but the physical layout is fundamentally broken. Parts are backing up in Station 3. Workers at Station 5 are standing around waiting for components to be driven across the facility.
Basically a logistical nightmare.
Exactly. And your solution to this broken layout is to just go out and buy a bigger 10,000 horsepower stamping press for Station 1.
Which is completely ineffective because the bottleneck isn't the machine's capacity to stamp parts. The bottleneck is the conveyor belt and the routing between the stations.
Right. The bigger machine just sits there idling faster.
I love that. Idling faster.
And sometimes, doesn't adding executors actually make the job slower?
Oh, absolutely. If your bottleneck is the driver trying to coordinate too many tasks, or say network congestion during a shuffle, adding 500 more executors just adds 500 more concurrent network connections competing for the same constrained resources.
They're just making the traffic jam worse. So what does this all mean for us? I mean, the core takeaway here is not that Spark cannot scale. Obviously, it scales to petabytes.
Right. The scale isn't the issue.
The lesson is that scaling worker nodes is only one move in a much larger game, and it's usually the wrong opening move.
If hardware isn't the fix, we need to understand what actually slows the engine down, and that comes entirely down to the execution shape.
Let's define that. Walk us through what Spark is physically doing. Not the logical plan on the screen, but the actual life cycle on the cluster.
Sure. So Spark's life is a continuous process of translation and division. It takes your query, optimizes it, and breaks that plan down into stages.
Okay.
And finally, it shatters those stages into individual tasks that can be handed to executor threads. But here is the secret of the execution shape. Once that planning is done, Spark spends a shocking amount of its life doing things that are not computation.
Wait, really? Not computation?
Yeah. It is moving data. It is materializing network boundaries, writing temporary files to disk, waiting on stragglers, and honestly, recovering from the simple fact that data is never distributed as cleanly as we mathematically want it to be.
Let's look at the classic example. A join followed by an aggregation on a huge data set. If I look at that on my screen, it feels embarrassingly parallel. I have a 10 terabyte data set. I have a massive cluster. Match the keys, run the sum, return the result.
But the moment Spark has to regroup records by a specific key, that embarrassingly parallel dream ends. because records that share a key do not naturally live on the same physical machine.
Right, they're scattered everywhere.
Exactly. To perform that aggregation, the data has to be completely reorganized across the cluster. This is the shuffle boundary.
Ah, the infamous shuffle.
Yes. Mapped tasks have to write their output to local disk partitioned by the target keys. Then, reduced tasks on other machines have to make network requests to pull their specific partitions from every single mapper.
Which means the network switches are suddenly lighting up like a Christmas tree.
They are completely saturated. The CPU is barely doing any work during this phase. It is just serializing data, writing to disk, and waiting on the network.
So local computation is essentially free compared to the cost of cluster-wide data movement.
100%. Once your job hits that shuffle boundary, the question is no longer, how many executors do I have? The question becomes, how expensive is the physical exchange I just forced the engine to orchestrate?
Okay, here's where it gets really interesting, because I want to push back on this a bit. I want to talk about the parallelism trap, because this catches a lot of incredibly smart, mathematically minded engineers.
Let's hear it.
Let's go back to my 10 terabyte dataset. Let's say I force that dataset into 10,000 partitions. Basic math tells me I now have 10,000 concurrent, bite-sized pieces of work.
Right.
If I have a cluster with 1,000 cores, shouldn't that sheer concurrency allow the engine to just chew through the network overhead and keep moving fast? Why does the math fail here?
Because the math assumes uniform distribution and zero administrative overhead. In reality, partition count does not equal balanced, useful work.
Okay.
If you force 10,000 tiny partitions, you don't necessarily get a speed up. You often just create a mountain of administrative bookkeeping for the driver.
Walk me through the mechanics of that bookkeeping. What is the driver actually doing that takes so long?
Well, for every single task, the Spark driver has to discover the work, schedule it, serialize the task closure, send an RPC call over the network to the executor, wait for the executor to deserialize it, and then track the state updates.
This sounds like a lot of steps for one tiny task.
It is. That scheduling overhead takes milliseconds. If your partition is so tiny that the actual data processing only takes 1 millisecond, you are spending more time marshaling task state over the network than you are executing your business logic.
You're suffocating the driver with administrative noise.
Exactly.
So we have the tiny task problem. But what if the data is just skewed?
That is the straggler problem, and it is the absolute killer of execution shape. Real-world data is deeply asymmetrical.
So true.
Let's say you partition by customer ID. One of those customers is a massive enterprise account that owns 40% of the rows in your dataset. The other 9,999 partitions are tiny.
I think I see where this is going.
Your cluster blasts through the short tasks in seconds.
Yeah.
And then 999 cores sit completely idle while one single worker thread churns sequentially through that massive enterprise account partition.
The cluster is essentially paralyzed by one hot key.
Exactly. You look at the Spark UI, and it shows a sea of green, finished tasks and one miserable, endless tail that keeps the entire stage open.
And if you add more executors at that point?
They literally cannot help you. They cannot jump in and assist that worker. That slowest partition is fundamentally too large, and it must be processed sequentially by one thread.
Wow.
This brings us to a crucial rule for your mental model. Spark's unit of scheduling, which is the task, is not the same thing as your unit of progress.
That is a critical distinction. The unit of scheduling is not the unit of progress. So the execution shape is heavily distorted by things like joins, shuffles, and skew. But the shape isn't just determined by what happens inside Spark's memory, right?
No, not at all.
It's heavily influenced by the boundaries where Spark meets the rest of the ecosystem.
Absolutely. The boundaries are where some of the most silent, expensive bottlenecks live. Yes, this one is incredibly common.
Because PySpark is the dominant way people interact with the engine today, PySpark is fantastic. It lets data science and engineering teams move quickly. But speed of development is not the same thing as execution speed.
Not at all. PySpark is essentially a Python API wrapping a Scala and Java engine. When you use standard PySpark functions, Spark translates those into optimized native JVM operators running over columnar data.
Which is incredibly fast.
It's blazing fast, but the trap snaps shut when a pipeline drops out of those native functions and calls a plain Python UDFA user-defined function.
But physically, Spark is carrying the data out of its optimized path, throwing it across a process boundary, waiting for a slower runtime, and dragging it back.
Exactly.
Which leads us perfectly into how we actually try to debug these problems.
Yeah.
Because these bottlenecks are hidden in the ecosystem, in the execution shape, across language boundaries. Engineers fall back on folklore.
Oh, the folklore, yes.
We use blind tuning, and we rely heavily on misleading dashboards.
Let's talk about the Spark UI. I want to offer an analogy for how we should view it. The Spark UI is not a single metric truth machine. It is a crime scene.
A crime scene, that is the perfect framework for it.
Think about it. If you walk into a physical crime scene and you see a shattered window on the floor, you don't arrest the window. The window is just evidence of what happened. It's the consequence.
But in the Spark UI, engineers will find a large number highlighted in red like high stage time, or massive shuffle read, or spilled bytes, and they immediately arrest it. They declare the metric itself to be the root cause.
Which is completely upside down. Let's take massive shuffle read. A stage with incredibly high shuffle read is not the root cause of your slow job. It is just the consequence of an earlier join shape you defined in your logical plan.
The shattered window.
Exactly. You forced a network exchange, and the shuffle read is just the receipt for that transaction.
Wow.
Or consider a stage with very low CPU utilization. A junior engineer might look at that dashboard and think, great, we have spare capacity. Let's increase the parallelism.
But it's not spare capacity, is it?
Nope. That low CPU metric is evidence of starvation. The executor threads aren't idle because they have free time. They are idle because they are blocked.
Blocked on what?
They are blocked on synchronous I/O waiting for an object store, or they are paused entirely by a massive JVM garbage collection event because you spawned millions of Java objects reading a bad file layout.
Makes sense.
Engineers who debug Spark at a senior level learn to treat every single metric purely as forensic evidence inside a much larger story about the physical plan.
Which means we need to debunk some of the classic tuning folklore right now. Because the reflexes people have usually treat the symptoms, not the disease.
Let's do it. Spark has many distinct failure modes because it is effectively many complex systems. A distributed storage reader, a memory manager, an RPC framework, a query optimizer, all wearing one single API.
Okay, let's bring all of this together. The goal of this deep dive was not to give you 10 tuning configs to blindly paste into your next pull request. It is about building a correct, rigorous mental model.
Exactly.
Once you can look past the illusion of your declarative code, once you can identify where data is physically being exchanged and whether the cost comes from network movement, from partition imbalance, or from language runtime adaptation, Spark stops feeling mystical. It becomes inspectable.
It becomes a glass box. And the sharper your mental model becomes, the less often you will reach for blind hardware scaling. You will look at a failing job, identify the bottleneck, and make one specific structural change to the plan that collapses the execution time. We will see you in Chapter 2.